Earth is surrounded by an invisible force that stretches far into space, shielding the planet from harmful radiation and cosmic particles. This force is the magnetic field, and although it is unseen, it plays a vital role in sustaining life and maintaining the atmosphere. Every day, the magnetic field protects us from charged particles emitted by the sun, which constantly stream through space. It shapes the auroras, those shimmering curtains of green and red that appear near the poles, a visible sign of its presence. These phenomena are not mere decoration. They are the result of a complex interaction between Earth and the environment beyond our atmosphere. The magnetic field is generated deep within the planet, in the outer core, where molten iron and nickel move in complex patterns. This motion creates electric currents, and those currents give rise to the magnetic field that envelopes Earth. Without it, life as we know it would be very different. Throughout history, the magnetic field has guided explorers with compasses, directed migratory animals across oceans, and allowed human civilization to develop navigation and technology. Yet, the field is dynamic. It drifts, weakens, strengthens, and occasionally reverses polarity entirely. In this video, we will explore the full story of Earth's magnetic field. We will examine how it is generated, how it has changed over millions of years, its protective role, how animals use it, and what the future may hold. By the end, you will understand why this invisible force is one of the most fundamental features of our planet. The Earth's magnetic field originates in the outer core, vast turbulent ocean of molten iron and nickel located nearly 3,000 kilometers beneath the surface. Temperatures in this region exceed 4,000 degrees Celsius, keeping the metals in a liquid state. The movement of this liquid metal, combined with Earth's rotation, creates a process known as the geodynamo. The outer core surrounds the solid inner core. As the planet slowly cools, iron solidifies at the boundary, releasing heat and lighter elements. These variations drive convection, currents of molten metal rising and falling. The Coriolis effect, caused by Earth's rotation, twists these currents into spirals, producing electric currents. These currents generate magnetic fields, which in turn influence the movement of the molten metal, reinforcing the field. The geodynamo has sustained the magnetic field for at least 3.5 billion years. Its presence is essential for life. It deflects the solar wind, prevents atmospheric erosion, and shields the planet from cosmic radiation. Even though the field at the surface is relatively weak compared to a refrigerator magnet, its vast scale allows it to extend tens of thousands of kilometers into space, forming the magnetosphere. The magnetic poles are not fixed points. The North Magnetic Pole drifts over time, influenced by changes in the flow of molten metal in the outer core. In the last century, it has moved from northern Canada towards Siberia at a speed of about 50 kilometers per year. Beyond drifting, the field sometimes undergoes full reversals, where north and south switch places. These reversals are recorded in ancient rocks. As molten rock cools, iron-rich minerals align with a magnetic field, preserving its direction in stone. Over millions of years, this record shows that reversals occur irregularly, with intervals ranging from hundreds of thousands to tens of millions of years. Reversals take thousands of years to complete. The field weakens, multiple poles may form temporarily, and eventually, the polarity stabilizes in the opposite orientation. During this time, the protective shield weakens but does not disappear entirely. Life has endured countless reversals, and there is no evidence that they cause mass extinctions. The field strength also varies independently of reversals. Measurements show fluctuations throughout geological time, sometimes stronger, sometimes weaker. Currently, satellites observe a slow decrease in field strength, but this is part of a long-term pattern and does not indicate imminent collapse. The magnetic field extends far into space, forming the magnetosphere, which shields Earth from charged particles emitted by the sun, known as the solar wind. Without this protection, the solar wind would gradually strip away the atmosphere, just as it did on Mars billions of years ago. The magnetosphere compresses on the side facing the sun and stretches into a long tail on the night side. It deflects most particles, trapping some in the Van Allen radiation belts, while allowing only a small fraction to reach the atmosphere. When these particles collide with atmospheric molecules near the poles, they create auroras, dancing lights that reveal the ongoing interaction between Earth and space. This protective role is essential not only for life on the surface, but also for technology. Satellites, power grids, and communication systems rely on the magnetosphere to mitigate the effects of solar storms. Even small fluctuations in the field can have measurable impacts on modern infrastructure, making it a critical factor in planning and risk assessment. Auroras are the most visible manifestation of Earth's magnetic field, interacting with the solar wind. Particles guided by the field collide with gases in the upper atmosphere, producing colors from green to red, blue, and purple. These natural light shows occur primarily near the poles, but can sometimes be observed at lower latitudes during strong solar storms. Auroras are more than a spectacle. They are a reminder of the invisible magnetic currents constantly shaping our environment. They trace the paths of charged particles as they spiral along magnetic field lines, offering scientists a way to study the field's structure and behavior in real time. Many species use Earth's magnetic field for orientation and migration. Birds, sea turtles, salmon, and even some insects rely on the field to travel thousands of kilometers. Studies show that animals can detect the direction and intensity of the magnetic field, integrating this information with visual and olfactory cues to navigate with astonishing precision. Sea turtles, for example, hatch on a beach and, guided by magnetic cues, travel across the open ocean to specific feeding grounds, sometimes returning decades later to the same location. Birds like the Arctic tern use the magnetic field to navigate from pole to pole, demonstrating that this invisible force is a fundamental part of Earth's ecological systems. Not all regions experience the magnetic field equally. Areas such as the South Atlantic anomaly exhibit unusually weak field strength. Satellites passing through these zones encounter higher radiation levels, and instruments must be shielded or temporarily powered down. Anomalies reveal that the field is not uniform. Local variations in intensity and direction provide clues about the structure of the outer core and the processes driving the geodynamo. They also highlight that while the magnetic field is stable on a planetary scale, It is complex and dynamic on smaller scales. Magnetic field is critical for modern technology. Navigation systems, from traditional compasses to advanced GPS devices, rely on the field for orientation. Satellites operating in low Earth orbit depend on the magnetosphere for radiation protection. Even power grids and communication networks can be affected by geomagnetic storms when the field is disturbed. Understanding the magnetic field allows engineers and scientists to design systems that account for fluctuations, ensuring resilience against natural hazards. As society becomes increasingly dependent on technology, the importance of the magnetic field grows, bridging ancient natural processes with contemporary human innovation. When the sun emits powerful bursts of charged particles, solar storms, they interact with Earth's magnetosphere. Strong storms can induce currents in power lines, disrupt satellite communications, and increase radiation exposure for astronauts in high-altitude flights. The magnetic field mitigates these effects, but monitoring solar activity and understanding field dynamics are essential for preparing for extreme events. The interplay between the Sun and Earth highlights the magnetic field's role as a dynamic, protective interface between our planet and space. Over time, the magnetic field will continue to fluctuate. Poles will drift, intensity will change, and reversals will occur. Scientists use satellite data and geophysical models to predict these changes, allowing society to plan for potential impacts on technology and infrastructure. Despite these variations, the field has been remarkably resilient over billions of years. It is likely to persist, continuing to shield Earth and guide life. Understanding its long-term behavior is both a scientific challenge and a practical necessity for maintaining modern civilization. If the magnetic field were to weaken significantly or disappear, Earth would face increased exposure to cosmic radiation and solar wind. Satellites and power grids could be disrupted, and the atmosphere could gradually erode over geological timescales. While life would not disappear overnight, the planet would be a more hostile environment. Migration patterns of animals would be disrupted, technological systems would require robust shielding, and the auroras would extend much farther from the poles, signaling a planet in a different magnetic state. This scenario highlights the magnetic field's importance as an unseen but essential force sustaining the conditions necessary for life and civilization. Earth's magnetic field is one of the planet's most remarkable features. Generated deep within the core, it extends far into space, guiding, protecting, and shaping life. It is dynamic, ever-changing, and recorded in stone, in ocean crust, and in the migration of countless species. Understanding the magnetic field allows us to appreciate the complexity of our planet, the delicate balance that sustains life, and the deep processes occurring far beneath our feet. Though invisible, it is a fundamental part of Earth's identity. A silent guardian, a guide, and a testament to the power of natural forces. In the sky, auroras dance as a visible reminder. In the oceans and skies, animals navigate with its help. In our cities and satellites, technology relies on it. The magnetic field is, quietly and consistently, one of the most vital forces shaping life on Earth.